Optical time domain reflectometry, or OTDR, is an effective method to characterize optical fibers and for detecting flaws in a network of fiber optic cables. It functions based on the principle that if photons are sent down a fiber, some will be scattered, largely due to Rayleigh scattering, while others will be reflected at varying locations thanks to defects, junctions, and splices. By measuring the time needed for photons to bounce off the imperfections and return to a detector, it becomes possible to calculate their locations knowing the speed of light in silica glass. Of course, because light travels at roughly 200 million meters per second within optical fiber, incredibly accurate timing electronics are needed to resolve distances on a useful scale. OTDR is also used to calculate the signal loss over a length of fiber or through various types of junctions, splices, connections, or interfaces. Conventional OTDR relies on a barrage of photons sent with each pulse, enough to ensure that the linear photodiodes used in such systems can register a signal. In order to guarantee a sufficient signal-to-noise ratio for a given laser peak power, the pulse width needs to be increased to overcome lossy fiber lengths or cope with lengths of fiber in the tens of kilometers or more. However, this leads to major drawbacks in spatial resolution and dynamic range. This is because the pulses of light must be relatively long in duration if longer fibers are to be inspected, up to 10 microseconds, which represents a train of photons 2 kilometers long. Shorter fibers can use shorter light pulses, but the resolution is still often measured in the meters or tens of meters. Conventional OTDR requires the user to make a trade-off between distance, spatial resolution, and measurement time. Single photon OTDR, also known as photon counting OTDR, avoids these shortcomings by eliminating the need for large numbers of photons to generate a signal. Sub-nanosecond duration laser pulses can be used, meaning that the first photon in a pulse is only a few centimeters ahead of the last photon. This in turn leads to dramatic improvements in resolution. It also leads to improvements in dynamic range, or the ability to detect small defects immediately following large ones. Each reflection point has its own probability of scattering a photon back to the detector. If a measurement is repeated enough times, typically a few million or more, which will take on the order of a minute, an accurate picture can be constructed of how likely each region in the fiber is to reflect a photon. This, in turn, can tell you where flaws are located, and also the signal loss over a length of fiber. The ID900 time controller is the perfect centerpiece of your photon counting OTDR setup. With a timing resolution as low as 13 picoseconds, it eliminates uncertainty in measurements. The ability to control both the laser source and detectors from a single screen makes setup and optimization incredibly fast and repeatable. The built-in histogramming function allows you to quickly visualize the effects of any changes made to test parameters while you zero in on the ideal settings. When it comes time to save data for later use, the ID900 software provides a convenient way to download both histogram and timestamp information. With the ID900, it is possible to perform single photon OTDR measurement using two different techniques depending on how the detector is driven, using rapid gating or free-running modes. The ID900 can be used to control the gate width and position in time with respect to the laser pulses. Even in free-running mode, a method called slow gating can be employed to scan or isolate a specific section of fiber. ID Quantique also produces a line of telecommunication wavelength single-photon avalanche diode-based detectors, or SPADs, which perfectly complement the ID900 time controller. Our newest model, the ID Cube, is available in both free-running and fast-gated versions and offers high quantum efficiencies and low dark count rates in a compact and competitively priced form factor. Moving beyond SPADs, our ID281 superconducting nanowire system provides unparalleled speed and quantum efficiency for the fastest measurements with the greatest possible dynamic range. Please visit our website at www.idquantique.com for access to datasheets and additional resources, or send an email to info@idquantique.com with any questions. We would love to hear from you.